Again, let's do a quick review because some students not coming yesterday. Okay. What's heap now? Okay. Either min heap or max heap, right? So the min heap, the parent always less than or equal to their children. Max heap, the parent, the value of parent will be always greater or equal to their children. Okay, that's the definition of heap. Heap may not be sorted. Okay, heap may not be sorted. But heap is leveraging well with what? With array. Because they want to leveraging well with array because array some certain advantage, right? They're able to access the elements by index very quickly, almost the constant time, right? So that's why. Besides before, we all learned the tree by the linked list, but now we're doing what? By array. Okay? So that's improve a lot of efficiencies. Okay? So we're using a heap. So also we learn what? Insert an element into the heap. Also to get the minimum and maximum value from heap. Also we extract the minimum and maximum value from heap. All right? Okay, that's what we learned yesterday. Question before we dig into the update? Okay, because this all knowledge is related. Okay, so when we do the insert, when we do the extract, we need what? We need a support function, support action. What support action we need? Either shift up or shift down to make sure after the operation keeps what? Keeps still the heap. Okay, so in the operation before and after, the data structure is still the same. Okay, that's just the principle. If you cannot adjust after operation, it's not a heap anymore. Okay, so we need to keep the heap. That's why we need support function shift up or shift down. All right, okay, let's go with the update. Okay, how to update the heap? For example, we get the min heap. Okay, we always mention about mini heap, but because mini heap we've been using a lot. Okay, in the future, mainly on graphics. Okay, so anyway, you guys can think about more, either using the Google ChatGPT to learn about maximum heap as well. Okay, regarding for this kind of the functionality operation, right? But okay, later on we use one of the maximum heap. Okay, but later on let's talk. Okay, this is a heap, right? Min heap. We want what? For example, we want update element 7 to 2. Just for example here. Okay, what do we do here?
You set 7 to 2 and you shift up.
Set 7 to 2 and then shift up. Yeah. Okay. So heap is work on array. Okay. Again, heap work on array, not. This is just a visualize. Help you understand. On computer, they won't have that. Computer have this stuff. Okay. All right. Okay. Oh, before we get into that, let's review again. It's important. How to find the parent? How to find the children on the heap?
2n plus 1, 2n plus 2, and
what?
n minus 1 divided by 2. 4 division by 2.
2. Okay, that's need to keep in mind. If you work on heap, you need to know about that. Okay, on array, point any element. Okay, you know index, right? Heap always accessed by the index. Okay, you know index, you can find the parent, or parent index. You also can find the left and right child index based on that formula. Okay, now 7 replaced by 2. Now we find the what? We find the index, right? 7, and then change to 2. Pretty straightforward, right? On array, right? Just change the number, right? Okay, and then we need to what? Shift up, right? Why we shift up?
Because it might be lower than its parent.
Yeah, okay. So now, if they shift up, we need to do what? Compare the value with what? With their parent. Okay, okay. So what's their parent index? 6, right? You can copy by yourself, okay? 0, 1, 2, 3, 4, 5. 5 minus 1. 4 divided by 2 is index 2. Okay? Now we find the parent. We need to what? Compare with the parent. We need to keep the what? Still mini heap, right? Do we need to what? Swap or not?
Well,
Yeah. We need to swap. Okay? And then what do we do here? Yeah, And then when you find this parameter, right? Because we need to swap. Okay. Do we need swap? Right? We need swapped. And then we're done. Okay. So now we, after shift up, become what? New min heap. All right?
Can that just be done in like a single while loop?
Single, yeah, yeah,
So
yeah.
you say while the parent node.
Yeah, that's right. Yeah, that's it. That's why have the good advantage of heap. Okay, that's why the design very smart. Okay, they're doing very smart design. Okay, yeah.
That would be like O of n runtime because it's.
No, this is not O of n. Let's discuss about the time complexity later. Okay, this is not O of n.
Oh yeah, because there's only half the branch.
Yeah, yeah. It's still log O of n. Okay. But two scenario, okay? Let's discuss about later, okay? So this is a shift up, right?
Yeah.
Is there any scenario to shift down? Is there any scenario to shift down on the update? Do we have any scenario? For example, let's find the 12, right? Replaced by 16. It's still shift up, right? Shift down.
13 would then need to be.
Yeah, this need to shift down, right? Okay. If this is replaced by 16, let's do swap. So it's based on the scenario, right? So first, what you can do, you replace, and then you need to decide it's either shift up or shift down. Okay, for the update.
And if it was shift down, you'd only need to do that once. You would need.
That's right.
You should check the left and right loop.
Yeah, left child, right child, which is the minimum number, and shift. And then swapped, not shift, swapped.
And then needs to be done after you.
Yeah,
That.
that's right, that's right. Now what they do here, find their child, right? Which is the smallest child? This one, okay, on the left child. And then we need to, what? Swapped.
And again, you would just check left to right.
What?
You'd always just check left to right. So if.
Yeah,
if the
yeah,
right-
yeah.
okay.
On the code, it's left to right,
Yeah.
but doesn't matter actually. As long as you find the smallest child. Okay. Even though they may have a chance, it's, both are lower than the parents, right? But you need to find the what? The smallest. Okay. Shift on the small, swap on smallest. All right. That's about the update. Right. This is done, right? Okay. Either shift up or shift down based on the scenario. This is the code. Okay. Code is pretty straightforward actually, right? You determine whether they pass what by the index you can update, okay? And then process, you design the old value and replace the new value, and then make comparison to determine shift up or shift down. That's all about. So we had the shift up code and shift down code, right? Yes, last lecture, just implement for that.
Wouldn't it be better to just have the sit down as the first check and then have it return immediately if it gets once it's true?
Return what?
Like if it sits down once, you just have it return immediately afterwards. Wouldn't that be
Yeah, it's you mean which scenario?
like
Shift
so
up or shift down?
shift down? Because
Shift
if
down?
it's shifting down, it would
Yeah.
only need to do that once and then it can return.
No, it may not be. Maybe multiple times. It's based on the tree, how big the tree is.
But if you're shifting down, you know that all of the roots above it are going to be smaller because you're only updating that node.
Yeah.
And it's already balanced from that point, so wouldn't you only need to check one shift down? And then
Now let's look at look at this example here. Same example. Okay, so if we replace 2 to 16,
Oh.
do not pay me. I just using one example here. That's way complicated. Okay, way complicated. We based from the simple example, but from if you replace 2 to 16.
You'd have to go.
You have to go to bottom, right? Okay. Make sense? Yep. All right. Okay. All right. Time complexity. Now, what do you think?
Log.
Still log n because why? Based on the this and this. Okay. this scenario to pass the index, you know which index need to be updated. But if the pass by value, for example, give you the value, what I want to update value in this heap to a new value. What the complexity?
Would it be
Log of n. Why? Because you have process search first. Okay, this is an unsorted search. So you have to, what scenario you have to visit all the nodes, okay, to find the match, a target node.
You chose n logging, so you have to find it and do it, or just
n,
n?
because this is the first is n, and then because log n, right? Log n is less domain than log n,
Yeah.
right? This is a class issue.
Because it would be O of n plus O of log.
Yeah, and then turn to log big O of n.
Yeah.
Okay. I did not put on the notes, not required for this lecture, but you guys know, you can know that. Okay. If you, yeah. Okay. All right. Okay, we did what? Insert. We did find the minimum value and maximum value. Also, we did what? Extract. This means delete, right? We did the update, and then we need to build a heap, right? Fundamental first step, we need to build heap. Okay, first, and then you can deal with the other operation. But you have to understand how this operation works, and then you know how to build a heap. Okay. They call the heap file. Okay, just give you the terminology: heap file, shop file, whatever file, right? So anyway, yeah, they call the heap file. So build a heap from the unsorted array. Give you array is unsorted. The first step you do to build the heap. Okay, reorganize the elements and come up with either min heap or maximum heap. Okay, once the heap built, and you can apply the operation, heap operation. All right. Okay. For example, this one. Okay, this is a heap. Is it a heap? No, not heap, right? Of course, it's not heap.
True.
Okay. What?
It would just be a tree.
Just a regular binary tree. Okay, regular binary tree. And then okay, so you look at it, I showed it first in this second, okay? But on computer, this is what you get. And okay, and then you visualize this way. Okay? But this I'm doing this way just to help you understand. Okay? So use Bradford traverse, you can get this way. The reason get the Bradford traversal, why? Because you can find the property parent children index. Okay, that's why we use the Bradford traversal. Make sense? We have a one node. We know. Okay, we can calculate the parents. We can get the left and right child. Okay. All right. Okay. Now, when you think how to build a tree, how to build a heap for this scenario, how to build a heap? Yeah, we need shift up or shift down. Where we start? First element.
Or you could
from
search
here.
for the lowest element, and then
Yeah.
You could have it return. You could take the min of that and then do a shift up from.
No, you don't have the mean because
sort.
it's not heap yet. You cannot find the mean. You know what I mean?
If you do a shift down from the top, maybe you could do this.
Don't think about shift down yet, okay? Because it's not heap. You cannot use shift down, okay? So all the function we learned before cannot apply yet because it's not heap. The first thing is you need to do a heap. Build this heap first.
Would it be best to find the lowest element and then, or sorry, just do sorted?
You sorted?
You sort the array and then
Sort the array? Okay.
rebuild from there.
Okay, let's yeah. It's good to think everything. Right? That's good. But here, let's go through the argument. The researcher, okay, created. Okay, very smart. What is this? So smart. Look at this node, the leaf node, right? Do we need to do anything? Yet, because you don't have children. Okay, you don't have children. Okay, so don't need to do anything. Okay, so for this one, how many of the entire array? How many elements in the entire array? Almost a half. Okay, it's 7. In total, it's 14, right? 7, 14. I didn't count. It's 13, 14. almost a half of node. We don't need to care about yet. What do we care? From where? From 7. From 7. Okay? Yeah, okay. Because they have no children, so we ignore. We start from 7. 7 have children, not? They don't have children. Okay? We do nothing, right? So this is all we do nothing. Now we move to 14. Okay? If you want to build the min heap, we need to do what? We need simple swap. Okay? Now we need simple swap. Because it can build a relation between parents and children. We know how to swap it. Okay? Yeah, if you want to build a max, you will what? Compare within whether great or not, right? If the min, you compare with the less or not, right? Something like that. Okay, if I want to build a min heap, 14, what are their children? Swap the smallest child, right? What are their children? 6 and 3. Which one we need to swap? 3. All right. Okay, swap is done for this one. Then what do we do here? Is that done? It's done. Okay. Then we wait till 15 now, right? Okay, 15. We need to swap or not? We need to find our smallest children, right? What are small children? 4, and then we swapped. Okay. You should look at this color, okay, how color shape. Okay? Yeah. And then what next? 13. Okay. Now what do we do here?
8.
We find the smallest children is 8, and then
5.
swapped. Okay. And then what next? Go to 18, right? Then what do we do here? Swap again, right? Swap. How we swap?
3.
What? 3, right? Find the smallest children is 3. Swap. Do we need to swap again for 18? Yeah. 6, right? And swapped. It's done? It's done, right? And then we do what? 11. 4, right? Swapped. And then do we need to swap again?
10.
Yeah, we need to swap again. Swap again. And then what do we do here? Go to what? 9. When you swap for 9? Yeah. 3, and then?
6.
6, okay. Okay.
Swap 6 and 9.
6, okay. No? Come on. Back and delay one slide, sorry. Yeah, you know this. It's swapped, okay? I swapped. Then it's complete. Okay.
Does it do that by just a queue, or does it just hold? Like,
What?
Does it work similar to a by search by stack?
That's just an array.
Okay.
Just an array.
Oh, okay.
You know what I mean?
Okay.
Just a single array. How amazing for that. It's really amazing. Okay. You just think about that, okay? It's so smart. It's fun. It's so smart. This is the code. Okay? Code. From almost half, okay, half minus 1, right? And then do the heap file. Do a heap file. So this is a heap file process for heap file. Right? Just a single while loop. That's it. Single while loop for what? For this array. Okay. We compare with the left. We got their children, left child and right child, right? And then got a candidate. What do they do here? Similar with what? With comparison, right? Comparison. Which way we need to swap, and then we process swap, and then to reassign the index of a candidate until this is equal to the candidate, we can break out. Okay, that's how the code works. Okay, all right. So this is something is learn very interesting. If you learn like a fundamental, like the logic work, right? A lot of library, how library build. That's backbone. So this is really fundamental. If you learn really deeply, it's like, wow, it's amazing. That's really amazing. I always compare the code I wrote. My code is just a piece of garbage compared with this one, right? Okay, just single array achieved. That's the okay. All right. Okay, build a heap. Once the heap built, and then you can do an operation. Okay, do the other what operation? Insert into a heap, extract, right? get minimum maximum, and then do the update. For the other function we just learned. Okay. Time complexity. What do you think time complexity for this one? For the build heap?
Logging?
What?
Would it be n squared? Yeah,
N squared?
Because you would have to, like, there's an instance where you have to, everything is unsorted and you have to go over it each time when you go down through.
Yeah. N squared, right? Yeah, if the n squared is this will be useless. Yeah, because it's what? It's a turn which problem? P problem, NP problem. Turn which problem? Yeah. So it's not NP. It's not NP problem. So it's potentially time complexity. It will be useless on real world. Okay. Actually, this complexity is not a big O of n squared. I thought you guys will say the n times log n because this is what n is half, right? Half size. This is regarding for sort of the what for the shift up or shift down. It's log n, right? Intuitively it should be n times log n, right? But it's not, okay? Let's compare here though. This is before, right? Before the become a heap. Now become heap, right? Look at the color pattern. Okay, so does this node, all the nodes being visited or not? Almost, except maybe this one and this one, right? Big O of n. Just intuitively is big O of n, okay? Big O of n. Do you guys still remember the first assignment, first question you asked? Remember for that?
It's not the same.
Yeah. It's not a filter type because it's based on the what index value. Index value time to update. Okay, that's good. Now let's see how to use mathematics way to calculate the time complexity, right? By the way, what is space complexity for this case?
B.
Yeah, big just single array. Okay, just single array. Big O of n o 1 or something. Okay. Okay, let's look at this node here. Don't look at this element, okay? Just look at the structure. In a way, for this one, how many elements in this level? N times n divided by 2, right? Okay. How much work they do when they process the entire like a building process, building the heap process? Cost at 0 because it's what? It's on the lowest, on the leaf node. Okay, on the leaf node. What about this level? N divided by 4, right? So how much work, what the cost being implemented at 1? All right? Okay, so it means you need from here to here, down one swipe. Make sense? Okay. Again, this one, what about this one?
I know where
8 by 2 until a root node. Root node, what's a root node? Just one root node, right? From root node until the bottom, how much work being done? How many steps being done, being swept? No, it's in general case. We are doing the mathematical, apply the general. What? Based on the mathematical model, mathematical way. What? Height. Okay, based on height. Height is log based on 2 of n minus 1. Okay. So in this work being done. Okay, make sense? This step makes sense, right? Okay. Okay, now let's dig into the mathematical model here. Okay. Okay, so 0 times 0 work done for the bottom, right? Times n divided by 2, plus 1 times n divided by 4, plus 2 times n divided by 8, plus until what? Log n minus 1 times 1. Okay, that makes sense for this step? That's the total work being done for entire building process. Okay, in worst scenario. Okay. Okay, makes sense, right? And then we summarize as a sum formula, right? Sum format. If divide a k, right? K from 0 until log n minus log 2 of n minus 1, right? This is what? K times 2 power k plus 1 of n. Okay, from this formula to get this formula. Make sense, right? Okay, so now we can grab the one. The k has 1, right? 2 n over 2, right? This is the constant, get out, right? And then we get this one. Okay, k times 2 power k, 1 over 2 power k. Okay, now we want to solve this problem, right? We cannot find the formula to solve, find the sum of that, and then we trigger in the upper bound. So the upper bound, what we can get for upper bound here, well, upper bound, we treat this if n is extremely, right? This will be the extreme large infinity, right? So it's the upper bound. Okay. Makes sense, right? This side. Okay. Now let's so from here we can get from here, right? K times same thing, same formula. K times put the k 1 over 2 over the k. Okay. The k just together. Okay. Now we get for what? We need want to build a formula for what? For this case. Okay. We put the 1 over 2 on top of the from sum. So will be become a 4 n over 4 and some function k times 1 over 2 and then the exponential k minus 1. Okay. We borrow a 2, right? 1 over 2, right? Okay, from this formula, what you can think about from this formula? Okay. Let's make assumption x equal to 1 over 2. So this is what n over 4. This formula will be k times x, k minus 1. Okay, what you can think about that? It's the derivative of x over k. Make sense? You still remember the calculus? Okay. Make sense? Okay, you will take derivative k, put it here, and then x k minus 1. Okay? That's a reverse way to think. Okay. Wow, this step is amazing. Okay, keep going, okay? And we know how to calculate this one, right? Geometric sequence. The formula we can get, okay? 1 over 1 minus x. Okay, take derivative. For this take derivative is equal to what? This formula take derivative. Right? So this is 1, right? That's not how to take derivative, right? And to here, right? And this become what? Minus 2. Okay. Right? Make sense? Okay. Now we plug the x 1 over 2 inside. Then we can big O of n, okay?
Didn't you look at that at the initial point where you pull out the n value and see that you're not going to get another value of n and just say that's O of n?
O of n, yeah. Yeah. Okay. Okay, good though. Let's look at the time complexity. Okay, so insert big O of log n. Minimum is big O of 1, right? Extract big O of log n. Update big O of n. Build big O of n. Big O of log n. Big O of n. So, okay. So this other operation, worst scenario is big O of n. Okay. This is good, right? It's good. So, all right. So from this feature, we can grab the what, minimum or maximum of from what? From array, right? Array list. What we can be using for from Heap? We can get a minimum or we can get a maximum very quickly. But to extend their usage, what we can use? We can create a new sort function. Yeah. Okay. We call it HeapSort. That's how the HeapSort come from. Because you keep tracking, right? Keep looping, right? You get the maximum or the minimum. You can get the sorted order of the list from unsorted. Okay. So that's how it works here. guarantee what n times log n? Why is n times log n?
Because you're
Building a heap and then
uh,
to abstract, to do abstract, right? To extract log n times log n. Makes sense, right? Okay.
Will it always be more efficient than like something like merge sort? Like,
Yeah, we'll compare. We'll compare. Okay.
merge
Is that
sort, it's kind of similar in a way.
similar? Yeah, similar. Yeah, yeah. But the n times log n in merge sort is the best scenario.
Yeah.
But this is the average scenario. This is guaranteed.
well, this would have less space complexity than
This is less space because it's all array,
merge.
right? And right. So it's so that's why it's good. It's really good. Okay, so that's why n times n. Why? Because it have the build n big O of n and then to extract. It's a what? Big O of log n. That's why it's a guarantee n times log n for complexity for sorting. Step: build a maximum heap sort from input array and then to repeat until the heap is empty. Okay. Repeat until the heap empty. How we do that? Swap the root max within the latest elements. Reduce the heap size by 1, and heapify the root to store the maximum heap the properties. So it means what? Reorganize array. This array itself. They didn't create a new array. Just reorganize the array itself using maximum heap to get what? Ascending order of a array. Okay? Make sense? No? Okay. All right. Okay, that's a code. That's a code. I need to be quickly, okay? So quick, okay? So it's what? First time to building the maximum heap. Okay? And then to what? One by one to extract elements from heap. They do what? Do a swap. Okay? And then do the heap file based on the rest of the array of elements. Okay? So they put the largest value to the end. Make sense? In array. So they still work on this array itself. They didn't create a new array. Okay? So that's why this is the amazing part. So they usually using the maximum heap to process the heap sort. Okay? If you want to do what? To have the descending, okay? Descending sort, use a min heap. Okay? That's how it works. Right? Okay. All right. Let's compare. Okay. Compare. Heap sort big O of n log n. Right. Let's focus on mainly about complexity. Okay. Quick sort. The average case big n times log n, and worst case is n squared. Right. And then merge sort n times log n. Right. So merge sort, but the space complexity equal to what? Big O of n. Right. But compare within the heap, just a single array. Right. So still. So the heap sort is really good, very efficiency, right? On the downside regarding heap sort is not a stable sort. It's not stable sort. Okay. All right. Okay. All right. Okay. Regarding heap sort, any question? No. Any other thing? Any other functionality or like a data structure we can use in the heap? Think about what has been learned before, because they what? They created the easy to get the maximum or minimum number. What other function? What other data structure we can using to heap to implement? Besides the sorting function, yeah, works. Is there any other? Okay, you don't know? Okay, that's fine. Product queue. Okay, product queue. That's two very, very common. Okay, common like data structures using by heap. Okay. Before we implement the product queue by what? By dynamic array. Okay, and then sort it, right? And then or linked list. This is what we did before, but now let's use the heap to implement. Okay, still remember product queue? Remember? No? Let's quick go through the. A product queue is an abstract data type similar to the regular queue, but each element have a priority. Okay, so once you add elements into product queue, you'll be reorganize this element to make this what? Priority. Or you assign as a priority for insert elements into the product queue. Okay, so they keep the what? Keep a sort of priority. So elements in the high priorities will be dequeued before the elements is low priorities. So high priority will be dequeued first. Okay, first in, first out. Okay. If the two elements have the same priorities, they sort based on the order in the queue. Okay. This is a priority queue. Let's compare. For priority queue, how we can using heap to implement priority queue? This is a function, common operation for priority queue, right? That we call the common function. In queue, DQ, peak, change, update the priority, change the priority, and then check whether it's empty or not, right? Once you have a queue, this is the common function. We want to implement this function by what? By heap. We want to implement by what? We learned before by what? By dynamic array and by linked list, right? But now we want to implement by heap. By heap, what do we can do equivalent in the heap? Heap function, we have insert, right? Insert, we have heap. And then we just do a enqueue print to insert within the heap. Okay? And then DQ to extract the minimum or maximum based on the what type of the order of the priority. Peak is what? Grab the first element, right? Grab the first element. So on the heap will be the either get the first element, right? Minimum or maximum. Exactly match the priority queue, okay? Change the priority, do the update. Check whether empty or not, just return whether empty or not, right? So all the main operation from heap kind of the equivalent to the priority queue. Perfect match. Make sense? Okay. So we learned before, compare with the heap, garbage. Okay, so heap, we use heap to implement the priority queue. That's better option. That's how the knowledge is like a rotation, okay? Want to achieve one goal, right? Always can be upgrade. And better. Let's compare. Okay, what we learned is sort of the not that good at heap. But not heap, for the heap, right? In queue, we can list again for the time complexity, right? Big log n, right? And unsorted is 1 and n, almost all the linear, right? And for the dynamic array, the insert almost has 1, all others is linear. But compared to that, the heap is better because they keep log n a lot. Okay? Makes sense, right? Okay. Good though. That's all about tree, okay? We're done with the tree. Okay. Maybe more though. For heap again. What other data structure you can think to use in heap? Besides the HeapSort and the priority queue. You can get the minimum or you can get the maximum. For example, the path finding. Okay, you can get the minimum pass, or you can get the maximum pass. Probably in most cases using minimum pass, right? So that's an intuitive. Okay, you can think. Okay, give you a problem, right? If that to require you to find the minimum number or best way to get the place. Okay, yeah, heap may work. Okay, just an intuitive. Like we learn a lot of this structure, right? You have an intuitive way to think. Okay, how to using the knowledge you learn to solve the real problem. All right? How to process search effectively. Okay? Well, binary search tree, right? You give a sorted sequence using binary search tree. That's very effective. Very efficiency to find the required.
No, but for the search, it wouldn't necessarily be a complete tree, correct?
Yeah, binary search will be complete. May not be complete tree. Yeah, may not be complete tree.
If search, it would be linked by certain nodes, but that doesn't mean that the other ones have nodes that go as far down.
Yeah, but just care about half for binary search tree, right? Because searching is more efficiency. They keep the log n. Make sense? Okay. So different scenario, think about different way to achieve, right? Okay. Okay, good though. All right. Okay, we are done with the tree now. Okay, so next lecture we're probably doing the hash table or map on set. Yeah, that'll be straightforward. Okay, map set based on knowledge we have been learned. They just build in library based on the knowledge we learned. Okay, all right.